Hey everyone, and welcome to ACA-Ali and ETEA in my pocket. I'm going to upload this video on my both channels, ACA-Ali and ETEA in my pocket. If you want to learn basic chemistry, then you should also subscribe to ETEA in my pocket, and if you want to learn chemistry of high level, then you should subscribe to ACA-Ali. Okay, today we're going to talk about vibrations in IR spectroscopy. My name is Ali Sudais, and I'm ETEA instructor, computational chemist, motivational speaker, and MD of ACA. Okay, you can see these things, they are moving to and fro. You can see this movement. This is called vibration. So we're going to talk about such vibrations today. Okay, we explained about the vibrations before, sorry, not vibration, we explained the IR before. And if you want to know about the basics, then you can go back to the first lecture and you can watch that video, and then you can come back to watch this one. Okay, now we know that the chemists always use the entire electromagnetic spectrum, like they use all of them entire. I mean, the chemists need everyone in here. This is the frequency in hertz. So they need everyone, and you can see this is the wavelength. The wavelength increases here. We give a mnemonic to people, and if you can watch that mnemonic, it's okay. If not, let me tell you here too. This is gamma from G. So the gamma is for girl, X, and just U for umama. Umama is also the name of the girl. V is, sorry, let me write here, very, and I for interested, and M for me, and R for ready well. Sorry, not ready well. Oh, name of a boy. So it says that the girl who is your ex. Wait, let me just make it different. The girl who is your ex, Umama, is very interested in me, Rahman. You can write it. I'm gonna say it again. The girl who is your ex, Umama, is very interested in me, Rahman. Okay, if you know the mnemonic, then you can remember the exact series, and exactly you can know that actually the ones on the left, you can see where it is. Okay, the one in here, you can see this gamma. This gamma, it has high frequency. What? It has high frequency but low wavelength, small wavelength. You can see the wavelengths, they are very small. You can see the difference between this and this, but you can see the difference between this and this is more than this one. You can compare this one, which means when we go from left to right, you can see they increase. It means the radio wave has the highest or the longest wavelength while the smallest frequency. Okay, as you know that the frequency and the wavelength, they have inverse relation with each other. So they have inverse relation, and therefore you can see that actually they are the opposite of each other. And sorry for this, they are the opposite of each other. When one increases, the other decreases. So this is how it works. Okay, now you can see that the nuclear excitation PET, core electron excitation X-ray, in X-ray crystallography, electronic excitation pi to pi star, molecular vibration. This is what we need, and we said that they have lower energy than the UV, while they have more energy than the microwaves. Okay, so you can see it, and UV visible, like they have low energy and high frequency. You can see the frequency of IR is more than the UV, while they have this, not the frequency, the wavelength, sorry, they have the more wavelength than the UV, but low frequency than the microwave. So that is what it makes it different from these two, and they have, therefore their interaction is different from that of UV and the microwave. Clear? Okay, now let's go to the next one. Okay, in time. First, I'm sorry for this, maybe it will take some time and I'll be back. I'm sorry for this, by the way. Oh, okay. So we discussed this, like, we go from the left right. When we go from left right, the wavelength increases while the frequency decreases. Now you know that the IR spectroscopic processes, right? You should know about this one, that what are the processes in IR. Let me remove this first. Okay, now you know that the quantum mechanical energy levels observed in IR spectroscopy are those of molecular vibrations. If you want to know about the quantum mechanical energy, then you can just go to the computational chemistry lecture and then you will find it there. Or maybe I'm going to make another video in detail very soon. Okay, we perceive the vibration as heat. Perceive the vibration as heat. When we say a covalent bond between two atoms of a certain wavelength, we are citing an average because the bond behaves as if it were a vibrating spring connecting the two. It means if there is a covalent bond, so we take it like this. So when you just see to this, and you will see this vibration in here, just see this vibration. You see the spring, yeah, yes. So therefore we say there is a covalent bond. I'm sorry. When there is a covalent bond and there is this bond, okay, you can see that there is this bond, but there is this to and fro moment. So we say this is actually like a vibrating spring. So there is like vibration. You see this vibration, and this is a diatomic molecule approximates an oscillating spring. So for a simple diatomic molecule, this model is easy to visualize. You can just understand from this molecule that there is vibration. Okay. Now the question is, what is a vibration in a molecule? What is vibration? So we're going to talk about the vibration is. If you see to this structure, you can understand from this structure that actually they are moving from one place to the other place, and we take it as an average. The vibration is actually that change. You can see there is the change when they come from here to here and here to here, and when they come back here and this like here, and they go away back. So this is actually the change. So we say any change in shape of the molecule, stretching of bonds, bending of bonds, or internal rotation around single bond. So different kind of changes happen in the form of stretching, okay, or the form of bending. We will explain this later. Bending of bonds, or internal rotation of single bond. So this is what vibration in molecule is. And why we study the molecular vibration? This is a quite interesting question, that why do we study these molecular vibrations? So you should know that because whenever the interaction between electromagnetic wave and matter occurs, in this interaction between these two, like the electromagnetic radio wave and the sample, which is the matter, when there is this interaction, there is a change. There is a change. And for example, there is this kind of vibration. It will increase or decrease this vibration. So therefore we study about the vibrations. Okay, therefore we need to study about the vibration, then we can know that what kind of change will be there. And okay, now you can see that the IR spectroscopic process is actually, there are in the vibrations, you can see that we have this bond vibration, and this bond vibration is of this kinda and this kinda. But before that, we explain this. I'm gonna tell you about some other things, and that is that there are actually the types of vibrations, and you should know that what are those types of vibration. We will explain one by one, and I have explained in one of my last videos as well. I'm sorry. Okay, the vibration is actually there are type. I'm so sorry. Okay, there are vibrations, and there are two types. Like the types number one, and that is called fundamental vibration. And the fundamental vibration is that vibration sorry, that's on the next page. I'm going to tell you, like the bending and the stretching is actually fundamental, and then we have non-fundamental. So non-fundamental is actually the vibration. These are the vibrations. These are the vibrations which, as a result of fundamental vibration, occur. Like a result of this fundamental vibration occur. Okay, so this is what the vibration is, and we can just say from it that we have two types of vibration. One is called fundamental, and the other one is called non-fundamental. Okay, now let's go towards the fundamental vibrations, talk about the fundamental vibrations. If you don't want to know about the types like fundamental and non-fundamental, so that is okay, there is no need. Okay, now let's see about the first one, is the stretching vibration. So this is the first one. So this is the vibration or oscillation along the line of the bond. Like this is the bond, it goes there and then here, and or it comes back, like you can see here, it comes back and it goes here. So this is also a kind of vibration which is called stretching. Okay, so we know that actually stretching vibration involves a continuous change in the interatomic distance along the axis of the bond between two atoms. So this is one atom, you see, this is one atom, and this atom, and this is another atom, and you see there is the difference. So you can see the moment. I'm going to show you the moment. You can see the moment. Yes, see the moment. It goes away from the nucleus, and it comes back to the nucleus, to the central atom. So you can see this is also a kind of stretching, and this is a symmetric stretching. Symmetric. Okay, this is called, keep remember, it requires more energy to appear at shorter wavelength. So it requires more energy, while the other one, it requires less energy. So you can see now let's see the next one, that is symmetric. You saw the first one. Now the asymmetric is the one in which one goes in one direction, the other goes in the another direction. It means one bond length decreases while the other bond length increases. That is called asymmetric vibration. Okay, so these two collectively, the symmetric and asymmetric, collectively, these two collectively actually they need more energy, so appear as shorter wavelength. Now now let's talk about the next one, and the next is bending. Now the bending is actually vibration as characterized by a change in the angle between the two bonds. Like the bond, when they come close to each other, the bond changes. So I'm going to show you, like you can see here, you see down in here the scissoring. This is called scissoring. Like you can see this one. Okay, see this one, and then I'm going to tell you, see, this is scissoring. When they come close to each other and then go away from each other simultaneously, so that is called scissoring. The next is rocking. So you can see the rocking. You can see the rocking. Yes, this is called rocking, which is in plane. They do not go out of the plane. When they are in X plane, Y plane, they are in the same plane. They do not go away from the plane. And the next you can see which is out of plane. So the one which is out of plane, you can see this one and this bond and this bond. We have two kinds. One is called twisting, the other is called wagging. Okay, it requires less energy. So I'm going to show you this one. Just see it. Okay, so these the bending actually requires less energy, so appears as longer wavelength. Okay, now we have symmetric and asymmetric. The first, you can see the interatomic distance between two atoms increases or decreases, as you can see it decreases, while in asymmetric, you can see in asymmetric, in this one, in the asymmetric, interatomic distance between two atoms is alternate or opposite. You can see this is called alternate or the opposite. It will alternate or opposite. So you can see it once again, and you can just you can get it. Okay. Then in plane bending, we talked that these are in plane bending. If all the atoms are on same plane, so that you can see the scissoring and rocking. The scissor and rock, you can see they're in the same plane, while the last one, you can see out of the plane bending, if two atoms are on same plane while the one atom is on opposite plane. So you can see the one is on opposite plane and the two are in the same plane. Okay. So if you just see in plane bending further divided into scissoring, you can see the scissoring and rocking. The two atoms move away or close towards each other at the same time. And in the rocking, change in angle between a group of atoms. Okay. Now, if you see to the last one, we have wagging and twisting. So these are out of plane bending, and these are divided as twisting, change in angle between the plane of a group of atoms, change in angle between the plane of a group of atoms, and then you can see the twisting. The twisting is actually change in angle between the plane of two groups of atoms. So you can see the difference between these two, and it's been given. Okay. Then you can beyond this, there are some of the other vibrations as well. Those are called non-fundamental vibrations. In non-fundamental vibrations, there is overtone, and we're going to explain this further. This is called overtone. There is overtone. What overtone is? These are observed at twice the frequency of strong bond. For example, carbonyl group, twice the frequency of strong bond. Then there is combination tones, weak bonds that appear occasionally at frequencies that are sum or difference of two or more fundamental bonds. So we call it non-fundamental. And the last one is Fermi resonance. If you do not need, so you shouldn't just waste your time and just learning this. Fermi resonance is interaction between fundamental vibration and overtones or combination of tones, like it happens in carbon dioxide. Okay. Then there is couple interactions and factors. So you can see that there are some of the couple interactions, but we don't need those couple interactions. And if you want to know about the couple interaction and the other things, you can just comment below, and then I can just explain to you that what these are. Okay. You can see in the IR spectroscopy, you can see the IR, the covalent bond oscillates. This is the oscillation of covalent bond, which is due to the dipole of the molecule. You see, this is the smaller and this is the bigger. When there are two atoms in which one is the smaller, the other is atom, then you can see. Let me show you that. You can see it, and there is a varying electromagnetic field is produced. You can see a varying. Yes. So the greater the dipole moment change through the vibration, the more intense the electromagnetic field that is generated. Okay, you can see, and it can tell you. Yes. Okay. Then you can see that the IR spectroscopy, in the IR spectroscopy process, when a wave of infrared light encounters this, you see, like first you should see, this is the diatomic. Okay, this is electromagnetic oscillating wave from bonding molecule. You can see this is the copper wave. Okay, this is the IR beam. It means it has vibration, its own vibration. Then you apply. If this is difficult for you, I'm gonna make it easy. This is its vibration, and then this vibration, they combine with each other, and it gives you a big wave, which we call copper wave. Okay. I think this will be easy now. Okay. So now you can know that what is the difference between these. You can see that now. Okay, electromagnetic wave from bond vibration. It means if there is a bond vibration So when there is a bond vibration, that vibration combines with the IR beam from spectrometer. When they combine with each other, it gives you a long amplitude, as we explained in the first one. Like this is the amplitude. Let me write it like this in here. It has an amplitude like this. This amplitude comes and it combines with this. When it combines with it, what happens? It comes like this in here, and this amplitude is changed into a long amplitude. So you can see the difference between this one, and then this one. See the difference, and then you can just tell this. Then you can say that what is the difference? Does the amplitude increase? Yes. So you will just notice that the amplitude has increased, and it is been coupled. Okay. So coupling is greatest when the coupled groups have approximately equal energies. Okay, and coupling between a stretching vibration and a bending vibrations occurs